Assalamualaikum warahmatullahi wabarakatuh. Hi, my name is AinaSofea binti Zazali. I am a final year student of Mechanical Engineering in University Technology Malaysia. The title of my thesis is The Comparison of Cavitation for Centrifugal Pump with or Without Volute Casing. My supervisor is Dr. Fazila binti Muhammad Zawawi. To kickstart my presentation, I will tell you the outline. Chapter 1 is Introduction. Introduction consists of type of cavitation, type of centrifugal pump, scope of work, problem statement, and objective. In Chapter 2, I will only discuss literature review. In Chapter 3, Methodology. Methodology consists of geometry of models, meshing process, and boundary condition. Chapter 4 is about result and discussion, and Chapter 5 will be the conclusion. What is cavitation? Cavitation is the formation and collapse of vapor bubbles in a liquid. The cavitation process occurs in two phases. First phase is bubble formation occurs at a point where the pumping liquid pressure is less than the vapor pressure. Second phase is the bubble collapse or implosion occurs at a point where the pressure will increase the above vapor pressure. Next, example of cavitation occurs in impeller blades of centrifugal. Next is type of centrifugal casing. There are three types of casing. The first one is volute casing, the second one is vortex casing, and the third one is diffuse ring casing. In my project, I will only consider volute casing. Volute casing is a spiral type casing which surrounds the impeller, increases the area of the flow, decreases the velocity of flow, increases the pressure of the water flowing through the casing. Volute casing improves the efficiency of the pump, but a large amount of energy is lost due to formation of eddies. My scope of work are NCCFX as simulation tools, 3D transient simulation, and dynamic mesh approach. Problem statement of my project are: the issues are head and efficiency breakdown. It is caused by cavitation, inaccurate prediction of cavitation development. The consequences are erosion, noise, and vibration. The solution is accurate prediction of cavitation development. The objective of my study is to simulate the turbulent cavitating flows inside a centrifugal pump. Next is to investigate the effect of calculation domain on the prediction accuracy of cavitation performance for hydraulic machines. Moving on to the literature review. The first journal that I have studied is the cavitation in semi-open centrifugal impellers for a miniature pump. The authors is XW Yu et al. In the year of 2008. The objective of the study is to study the cavitation performances of miniature pumps. The finding shows that the miniature pumps have similar cavitation performances as an ordinary size pump, with the cavitation performances of the semi-open impeller reduced by increased axial tip clearances. Next journal is partially average Navier-Stokes method with modified K-epsilon model for cavitating flow around a marine propeller in a non-uniform wake by B.J. et al. In the year of 2011. The objective of this study is to pursue more accurate estimates of unsteady cavitating flows with large-scale fluctuations at a reasonable cost. The study finding confirmed from the simulation by the PANS method with Fk equals to 0.2 that the whole process of cavitating flow evolution around the propeller in non-uniform wake can be very well produced, including cavitation inception, sheath cavitation, and top vortex cavitation observed experimentally. The last journal is Numerical Studies in a Centrifugal Pump with the Improved Blade Considering Cavitation. It is by P.F. Song et al. In the year of 2017. The objective of the study is to improve the micro-high-speed centrifugal pump cavitation performance and to understand its internal cavitation characteristic. The result shows that the modification of blade profile curve of suction side can improve the cavitation performance of an impeller and hydraulic efficiency of centrifugal pump. Compared with design impeller, the critical cavitation number of centrifugal pump with modified impeller decreased by 26.5% under the same flow rate coefficient, and thus cavitation intensity in the modified impeller is weakened effectively. Next is methodology. The first step is problem identification. It is from define the goals and identify the domain. Next step is pre-processing, which consists of geometry, mesh, physics, and solver settings. Next step is solve, compute solution, and the last step is post-processing, examine results. Now I'm going to talk a little bit about the geometry for Model A, which with the volute casing. Number of blade chosen is 8, rotational speed is 2100 rpm, the thickness of blade is 0.02, blade angle is 22.5 degree, hub blade angle is 27 degree, shroud blade angle is 16 degree, casing rotational degree is 14 degree, and the section type is circular. This is the model that I have designed from ANSYS. This model is called Model A. Next is geometry for Model B, which is designed without volute casing. Number of blade is also similar with Model A, which is 8. Rotational speed is 2100 rpm. Thickness is also similar, 0.02. Blade angle, hub blade angle, and shroud blade angle are also similar with Model A. This model is named as Model B. Next is the meshing process. So in the figure below is the result of meshing process for Model A. As we can see, the node is 208195, the triangles 112838, the quads 28370. Meshing process for Model B, it has node of 75223, triangle 108676, and quads 17083. Notice that Model A has more nodes compared to Model B. This is because Model A has more complex design in comparison with Model B. The fixed geometry dimension is the mass flow rate, rotational speed, and speed of the pump. ANSYS preprocessing include mesh generation process and boundary condition specification, and the data analysis include head coefficient, Thomas cavitation number, and cavitation specific speed. The boundary condition for both models are: the turbulent model is set to be k omega, shear stress transport. The angular velocity is set to be 2100 revolution per meter. The material, since this is a cavity condition, it needs water liquid at 25 degrees Celsius and water vapor at 25 degrees Celsius. The saturation pressure chosen is 3169 Pascal. The inlet is set to be bulk mass flow rate. The mass flow rate is 35 kg per second. The outlet is set to be static pressure with 25000 Pascal. Now, I'm going to talk about the results and some discussion. This is the calculation for Model A. The NPSH is 13.02 meter. The NPSHR is 2.58. This value is given from ANSYS. The NPSHA is 10.79. The Thomas cavitation number is 0.65 and the head coefficient is 0.6. This is the calculation for Model B. The NPSH is 11.62 meter, the NPSHR is 2.58, and the NPSHA is 37.63. The Thomas cavitation number is 0.58 and the head coefficient is 0.6. The cavities form at the domain inlet with reducing total pressure for models A and B. The initiation of cavitation happens on the suction side of the blade. Both findings of the two models indicate high efficiency since it does not consider mechanical errors. And asymmetry also occurs at tiny numbers of cavitation in the static pressure distribution for Model A. This is the result for Model A and Model B. The color represents the pressure. The length of the cavity between the blades for Model A is approximately twice that for Model B. This large cavity can cause extreme blockage of flow in the impeller and lead to a sudden drop in pump output. These are the formation of cavity for Model A and Model B. As for conclusion, a remarkable symmetry feature of turbulent cavitating flow exists in the centrifugal pump when steady simulation is conducted by using the calculation domain with volute casing. The asymmetrical features of cavitation development in the pump is caused by the interaction between the impeller blade and the volute casing tongue. Steady calculation overestimates cavitation development using the calculation domain with volute casing. For engineering application, the calculation domain with single blade-to-blade flow passage is preferable for steady cavitation prediction in centrifugal pump. These are my Gantt chart for UGP 1 and UGP 2. That is all for me. Thank you.